All right, so today we're going to talk a little bit about vector spaces. So vector spaces are going to kind of be the playground that we're using in linear algebra. And we're going to also talk about some of the usual suspects. So the idea with this section is we're going to talk about kind of what a vector space is. We're going to see a bunch of examples of vector space. And I want to try to highlight for you guys what the most important vector spaces for you guys right now to know about are. If you ever move on to, say, grad school, or you move on to some other various fields, we can see many different examples of vector spaces, and we're going to kind of deal with three major ones in this class. So in Lab 2, this is the radiography and tomography Lab 1, but this is the first lab, or the second lab rather. We notice that if we add two images together, we're going to get a new image. We're also going to see that if we multiply an image by a scalar, we'll get a new image. And so this kind of gives us the idea that we can get a bunch of different images just from the ones that we had, and we can combine images in order to get new images. And this idea is going to be something that we're going to kind of explore a little bit going forward. So remember, an image is a finite ordered list of real values with some sort of geometric array description. So we kind of have that for our, if we're looking at these images, we have an ordering to the way that we discuss that information, and we can add them and we can multiply them by scalars, and those are things that we're able to do, and there are some kind of nice properties we get from that. So let's move on then to maybe a little bit of a more formal definition for vector spaces. So the word vector might be familiar if you've taken vector calculus or physics. In those courses, there's a specific type of vector used, vectors in RM. That is, the word vector might bring something specifically to your mind. So you might think of something that looks like AB, ABC, or A1 through AN, or any of these other different versions of what you might think of as a vector when you hear that word. We're going to first define what sort of thing we want to talk about when we're talking about linear algebra concepts, and then we'll discuss the elements in the sets that we're working with that are called vectors. So let's give some definitions. A set V with a set of scalars and operations plus and scalar multiplication dot is called a vector space if the following 10 properties hold. Elements of V are called vectors. We're going to let U, V, and W, B, and V be vectors, and alpha and beta be scalars for these different definitions. So the first of these properties is that V has to be closed under addition. In other words, we're saying that if we have two vectors U and V that are already in our set, then their addition, U plus V, has to also be in the set. So adding two vectors gives a new vector in the set. V is closed under scalar multiplication, so alpha times a vector. So if we have a scalar and we have a vector U that's already in the set, if we multiply it by some scalar, that new vector will be in the set as well. So just kind of a question here. Does the set of odd real numbers satisfy those two properties alone? So if we looked at specifically odd real numbers, it's not going to satisfy that property. So no. Example, 1 plus 3, both of those are odd, is going to equal 4, which is not an element of the odd real numbers. So that's not going to work out. What if we looked at even real numbers? Well, if we look at the addition, that'll work. But if we look at multiplication, so scalar multiplication, say I take 2, which is in the set of even real numbers, and I multiply that by a half, that's going to be equal to 1, which is not part of the set of even real numbers. So these two kind of very common sets we're used to dealing with, odd real numbers and even real numbers, don't count as vector spaces because they can't even satisfy the first two properties. These first two properties we're going to call the closure properties. Because the idea is that it's closed under addition and scalar multiplication. In other words, if you take things that are already there and you add them together or you multiply them by scalars, you'll get something else that's also there. The next five properties are going to be known as the vector properties. And these are things that, for the most part this semester, you can take for granted. So some of the ideas here, addition is commutative, so if you take u plus v, it's the same as v plus u. It's associative, so if we take and add u and v and then add w, we get the same thing as if we add v and w first and then add u to it. Scalar multiplication is associative, so alpha and beta here, if they're just scalars, we can take alpha times the quantity beta plus v and make that the same as alpha times beta plus v. We also get that scalar multiplication distributes over vector addition. So alpha times u plus v is going to be the same as alpha times u plus alpha times v. And vector multiplication distributes over scalar addition. So alpha plus beta times v will be the same as alpha times v plus beta times v. So again, you might be looking at these five and thinking, well, yeah, of course those are all going to work. And for the most part this semester, you're going to be able to get away with that. If you ever went to a grad school course, that's where things are going to maybe start having more difficulty, where the rubber meets the road. So these are ones you don't have to worry too much about. The last three properties are going to be known as the identity properties. And so here, we kind of need to have these different identities. So v contains a 0 vector, where 0 plus v is the same as v plus 0 equals v. So in other words, something plus a vector equals that same vector, and that would make that something the additive identity. So here, when we're talking about this, note that the additive identity is not necessarily 0. So, for example, let's say I had real numbers. So if I took 1, 2 plus 0, 0, and that's going to be the same as 1, 2. So this would be the additive identity. For whatever set of vectors this is. But notice it might not just be the number 0, it might be, say, a vector of zeros. It also has additive inverses. So if I have some sort of vector, there is a negative version of the vector which I can add to it to get the 0 vector. So note that we can kind of get this from some of the stuff above. We're told that we have the ability to be closed under scalar multiplication. So if I have a vector, I can multiply it by, say, -1, and then I should get the additive inverse. And so if I then add the vector plus -1 times the vector, I should get 0. So that's usually one that's pretty easy to get if we're talking about bigger vector spaces. We'll see some weird examples where that doesn't always happen. We don't always get those, but it happens often. And then the scalar set has an identity element 1 for scalar multiplication. So in other words, I can take 1 times a vector, and I get that vector for all vectors in that set. If we were in a graduate level class, sometimes that would be something other than the number 1. You're not going to have to worry about it being other than the number 1. We try to be very careful with this in case we have some math majors in the course, but in the end, this is not going to be something you're going to have to really worry all that much about. All right, so we're going to do this careful thing because Basically, it's saying that it's not always going to be the number 1, and the 0 vector is not just a number 0 or the vector of zeros every time, but you can ignore this for this course. We put this disclaimer in there in case you're doing like graduate level things, but you don't need to worry too much about it. So notice that the elements of a vector space are called vectors, but they don't necessarily need to look like the vectors we had before. So here's our first vector space we're going to have and look at. And there's a lot of argumentation here as to why a lot of these properties exist for them. I'm only going to mostly focus on the closure ones and the identity ones. So the first common type of vector space example is going to be that of Rn. So Rn is the set of points or vectors in n-dimensional space with scalars taken from the set of real numbers. Here we're recognizing that addition of two vectors is component-wise. So when this is going to be similar to how we had things with our images. We took and each of those different components, we added them, or our matrices. When we added those component-wise, we were able to figure out how addition worked. So examples of this might be 1, 0, or 1, 2, or pi square root 2, or a bunch of different things. As an example, we could have just R, or R1. The set of real numbers is a vector space with scalars taken from the set of real numbers. It's going to define addition and multiplication, all the ways we're used to. So example vectors in R will be things like 1, 2, 5, 7, -2, pi, things like that. So as long as they're real numbers, we can take any two real numbers and add them to get another real number, and we can take any real number and multiply it by a scalar. In this case, we're using the scalars as more real numbers, so you can take a real number, multiply it by a real number, and you still get a real number. This becomes a lot more interesting if you talk about complex numbers, because not all of these things hold so well. We're not going to worry about that today. So this example kind of goes through all the different reasons why all 10 of those properties works. I'm going to focus on the first two and the last three. So the first is that it's closed under addition. So let's talk about that. If we take two vectors where I know u1 and u2 and v1 and v2 are all are each going to be real numbers, then u1 plus v1 is a real number, and u2 plus v2 is a real number. So in other words, we take a vector of real numbers plus a vector of real numbers, we get a vector of real numbers. So it's closed under addition because the new vector will also be in R2. V is also closed under scalar multiplication. So if we take a real number and we multiply it by a vector that has real numbers, the new vector also has real numbers in its entries, and so we get R2. Things that probably aren't so surprising: addition commutes. So you can take and switch the order. It's associative, so you can take a grouping like this plus another vector and then switch where the grouping is. Scalar multiplication is associative, so we can take these and pull out and multiply those scalars together. We also have distribution for scalar multiplication and over scalar addition, and then it's just some kind of the big other ones, the identity properties. We have a zero vector, so 0, 0 plus a vector of real numbers is going to be that same vector of real numbers. We have additive inverses, so if we have a vector of real numbers, we add that same vector but with negatives instead, we get back that zero vector. And then if we take a vector of real numbers and multiply it by the scalar 1, we get back that same vector of real numbers. So if we want to show a set as not a vector space, we need to show that just one of the 10 properties fail. So let's consider looking at this set of vectors. So this is not going to be a vector space. I want you to think a minute as to why. So maybe pause the video here, although let me say one thing before you pause the video. When we're looking at these, note that it's just these 5 elements. So things that are not in V are things like 3, 3, 1/2, 1/2, -5, -5. We only have these 5 elements here. So which of these properties is going to fail? So now maybe pause, take a moment and think about it. All right, I'll assume you've paused. So let's take a look then. So closure under vector addition, the idea that if we take and add 2 of these together is not going to work, because if I take -2, -2 plus -1, -1, that gives us -3, -3. But if you notice, this is not part of our set V. So it fails closure under addition. However, it does have an additive identity, right? If I take any of these and add 0, 0 to it, I get back whatever I had. And it also has additive inverses for each of those vectors. So if I take -1, -1, plus 1, 1, I get 0, 0. If I take -2, -2, plus 2, 2, I get 0, 0. If I take 0, 0, plus 0, 0, I get 0, 0. So we want to think about what we would need to add to this set to make it a proper vector space. And there's kind of a little bit of a hint here. So we notice we have this pattern of needing to have the same entry for both parts of our vector. And so we'd want to go ahead and add vectors of the form A, where A was an element of the real numbers. So that would mean that we could have these things all work out. Now, notice I didn't say integers, right? Because these are all integers. But if we fail to make it all real numbers, we have a different property breaks. So I want you to think about this for the discussion board. What property, or maybe properties, break if we only add vectors AA where A is an integer. So I want you to think about that, maybe talk about it a little bit on the discussion board. So this is the first type of vector space that we have to work with. There's 2 more common ones. So Rn is going to be something that we deal with a lot. The 2 other ones that we're going to deal with very commonly are going to be M2 by 3, or sorry, not specifically M2 by 3, but matrices, so M by n, and polynomial spaces, Pn. So we'll talk about these in a little bit. And we'll talk about polynomial spaces in a bit. We'll talk about matrices now. So an example space here would be M2 by 3. So this is matrices that have 2 rows and 3 columns where every entry is in the real numbers. This is a vector space when you have addition and scalar multiplication defined the way we've been doing them. So in other words, if we want to show closure under addition, and I've got A1, B1, C1, D1, E1, F1 plus A2, B2, C2, D2, E2, and F2 added together, our entries are going to be A1 plus A2, B1 plus B2, C1 plus C2, D1 plus D2, E1 plus E2, and F1 plus F2. And so notice that these entries are in the real numbers, and so this is something that's in M2 2 by 3. Now, it's also closed under scalar multiplications, because if I took a scalar and multiplied it by this matrix, I get alpha A, alpha B, alpha C, alpha D, alpha E, and alpha F. And since these are all going to be real numbers, we get that this is a 2 by 3 matrix with real numbers. And so this is also an M2 by 3. So all the vector properties are going to hold. Like I said, those are not things that I'm really expecting you to be focused on and checking all that much, but they are necessary. So we just need to check for additive identity, additive inverse, and scalar identity. So scalar identity, like I said, is normally going to be 1. Additive identity is going to be just a matrix of zeros. And if we want the additive inverse for some vector A, B, C, D, E, F, I think you guessed it, all we have to do is negate A, B, C, D, E, and F. So -1 times that matrix will give us the additive inverse for the matrix. So notice here that even though these are matrices, because we're talking about matrices as a vector space, we're going to call them vectors. This is probably one of the biggest hurdles early on. There are a lot of big hurdles in this class. One of the biggest ones is understanding that we need to go ahead and treat these and talk about these as vectors. All right, let's look at another common space before we kind of start delving into some of the less common things, just so you can see more examples and understand what makes a vector space a vector space. So let's say we want to look at polynomial spaces. So polynomial spaces are going to be a0 plus a1x plus a2x squared plus a3x cubed, all the way summing up until an x to the n, where a1 or a0 through an are in the real numbers. So this is a vector space where basically we're saying it's a polynomial of degree at most n, where we are taking addition and scalar multiplication the way we would normally for polynomials. So example, if we're looking at P2, we can say that that's the set of all ax squared plus bx plus c, where a, b, and c are real numbers. And so the polynomial has degree of at most 2. And so some examples of this might be x squared minus 2x plus 5, or 10x squared plus 7x, or say 3x minus 3. So notice that the degree here is at most 2. So when we're talking about these a, b's, and c's, for the first one, a would be 1, b would be -2, and c would be 5. For the second one, a would be 10, b would be 7, and c would be 0. And for the last one, a is 0, b is 3, and c is -3. And so as long as we have a degree at most 2 in P2, we're in that vector space. So would x cubed then be in P2? No. Its power is too high. So we're never going to be able to figure out how to get an a, b, and c to describe x cubed for us. But x cubed in P3? Yes. There, its polynomials of degree at most 3, and so x cubed on its own is something that is in P3. So we want to talk about why polynomial spaces are vector spaces. So here, it's closed under addition. So let's look at P2 as an example here. We look at a1x squared plus a2x plus a3 plus b1x squared plus b2x plus b3. We'll get a1 plus b1 x squared plus a2 plus b2 x plus a3 plus b3. And so note that all of these a's, a whatevers plus b whatevers, are in the real numbers, and our degree is still at most 2, and so this is going to be something that's in P2. We're also closed under scalar multiplication, so if I take some alpha times ax squared plus bx plus c, I get alpha a x squared plus alpha b x plus alpha c. And so notice that alpha a, alpha b, and alpha c, all three of those are real numbers. And so this is also degree at most 2 polynomial. And so this is also going to be something that's in P2. Okay, so we've got that going for us. We want to look then at the vector properties. So the vector properties are something that we're just going to get. Again, we're not going to concern ourselves in this class too much with those. We want to talk about the additive identity, scalar identity, and additive inverse. So our scalar identity is going to be, as usual, 1. We take and multiply by 1. We'll get whatever polynomial we're looking for. If we want to look at our additive inverse, we need to first know what the additive identity is. It's going to be 0 here, which is, you can just think of as 0x squared plus 0x plus 0. This is definitely something that's in P2. And so our additive inverse for ax squared plus bx plus c will be negative ax squared minus bx minus c, which is also something that's in P2. Okay, so those are going to be our three main common vector spaces: real valued vectors, Rn, matrices, Min, and polynomials, Pn. Now notice in polynomials, the things we're worried about mostly are going to be the coefficients. These x squareds, x's, and whatever the constant term is, this is usually just going to be a placeholder for the things we're looking at. So that'll be something to keep in mind as we go forward. All right, we'll talk about a few more vector spaces in this video, but if you think you've got a comfortable handle on what makes something a vector space, I'd actually recommend stopping the video right here. The rest of what we're going to do is just going to show a couple of different things that make something a vector space. Or rather, maybe instead of stopping the video here, you should skip ahead to when we talk about common vectors or homogeneous systems of equations. So maybe kind of find in the video where that is. Hopefully I'll post a timestamp for that so you can just kind of click to that really quickly. But those first three are going to be our main vector spaces we're dealing with. So this is just if you need to see a little bit more of what is a vector space. All right, so we're also going to have that function spaces are a vector space. So a function space is going to be, for us, the set of all functions that go from the real numbers to the real numbers. So anything whose domain is the real numbers and whose range is a subset of the real numbers. We're going to take and define addition and scalar multiplication the way we normally do. And so here, anything that goes from the real numbers to some sort of range that's a subset of the real numbers is something that is going to be part of the function space. So examples: f of x equals e to the x, g of x equals x, h of x equals cosine of x, or even say k of x equals 0. All of these are different things that could be considered to be in our function space. And so their domains are the real numbers, and they output to somewhere in the real numbers. And so we can check all of our properties. The first two and the last three are going to be the ones we focus on. So if we have two functions that go from the real numbers to the real numbers, if we add them, they still are going to go from the real numbers, and then they're still going to output real numbers. So we're still going to get some function that has that domain and range that we're looking for, and so it's closed over addition. Similarly, if we look at scalar multiplication, if we take a function whose domain is the real numbers, we multiply it by a scalar, that doesn't change. It also doesn't change that we're outputting to real numbers. Ignoring these next 5 properties, going down to the 0 vector. So for us, the 0 vector is going to be a constant function z of x equals 0 for every x in the real numbers. And so if we take z and add it to the 0 function and add it to another function, we'll just get back whatever that function was. So that'll be our 0 vector. So if we want to go ahead and get our inverses, we'll just take -1 times our functions and then add those together in order to get that 0 vector, 0 function we were talking about. And if we take the real number 1, our scalar, and multiply it by a function, we'll get the same function. So for functions, everything works the way we want it to. Everything's hunky-dory. Alright, we also can talk about grayscale images as a vector space. So notice that the set of images with a specific form are going to make a vector space with scalars taken from R. That is, if we consider this matrix or this image below, this is going to be a vector space since addition and scalar multiplication are both going to work for us, and there's a corresponding real number to each individual pixel or voxel, however you want to call it, and we'll end up getting all 10 of the properties that we're looking at, which is great. Let's look at an example here. So let's say we just had this set here of containing just the 0 vector. We want to know whether or not this is going to be a vector space. So maybe pause the video here, think about it, and then determine how you feel. All right, you got it? Great. So let's say we want to go ahead and look at this vector space. Does it have the 0 vector? Yep, it has our additive identity. If we take something in here and add it to something else in here, do we get something in here? So if we take 0, 0, 0 plus 0, 0, 0, do we get that? Yep. If we have this times a scalar, do we get something that's in the set? We absolutely do. If we take this times 1, do we get it back? You bet. Is there a way to add something to this in order to get the 0 vector? Yeah, the 0 vector. So this actually has all of our properties for a vector space. Is it interesting? No, except for the fact that it is a vector space. So that's really neat. All right, so let's look at, say, 2 other examples. So we want to determine whether or not this subspace is going to be a vector space. So here what we have is a set of some vectors, and we have conditions on those vectors. So we need to satisfy these equations. And so once we know how we satisfy those equations, we can then try to figure out whether or not our properties are satisfied. So what we need is we're going to take these and find solutions to this system of equations. Okay, so that means we have to look at the set of equations x plus y plus z equals 1, 2x plus 2y plus 2z equals 2, and negative x minus y minus z equals negative 1. So this is not homogeneous. So I think we may or may not have seen before. A homogeneous system of equations means that all of these are equal to 0. So homogeneous system, all equations equals 0. So let's take a look at this. If we put it into a matrix, 1, 1, 1, 1, 2, 2, 2, 2, and negative 1, negative 1, negative 1, negative 1. And if we solve this system, RREF, we'll get 1, 1, 1, 1, 0, 0, 0, 0, 0, 0, 0, 0. So then, using what we know then from discussing our solutions to systems of equations, we have that x plus y plus z equals 1, or in other words, x equals 1 minus y minus z. And here, y and z are our free variables. So that means we can rewrite this above set as being the set of all x, y, z, such that x equals 1 minus y minus z. And we can go even further and replace x with 1 minus y minus z. And so we can make it be 1 minus y minus z, y, and z, such that y and z are in the real numbers. We could even rewrite it as 1, 0, 0 plus y times negative 1, 1, 0 plus z times negative 1, 0, 1, where y and z are in the real numbers. So something we'd want to go ahead and check, we want to know whether or not it's closed under addition. So closed under addition. Let's say we took two vectors that are in here. So say we looked at 1, 0, 0. That's a vector in this set. And we added it to the vector 1, 0, 0. That'll give us 2, 0, 0. But 2, 0, 0 is not an element of this set V. So this is not a vector space. Okay, so we have something that's not a vector space. Let's see if we can go ahead and determine if we change this to a homogeneous system, so now all of these equals 0, whether or not we will end up getting something that is a vector space. So let's take a look here. Same thing as before, we want to take our system of equations, x plus y plus z equals 0. 2x plus 2y plus 2z equals 0, and negative x minus y minus z equals 0, and we'll turn it into a matrix, 1, 1, 1, 0, 2, 2, 2, 0, negative 1, negative 1, negative 1, 0, and we will go ahead and put it into reduced row echelon form, and get 1, 1, 1, 0, and then a bunch of zeros below. So this then tells us that x will equal negative y minus z, and y and z, which are free variables, are going to be in the real numbers. So then we have V is the set of x, y, z, such that x plus y plus z equals 0, which is going to be the set y times negative 1, 1, 0 plus z times negative 1, 0, 1, such that y and z are in the real numbers. So this is a little bit weird of a space to think about. We can still probably check these properties, right? Yeah, so let's do that. So if we take looked at closed under addition, if we have some x1, y1, z1 that's in V, and we have some x2, y2, z2 that's in V, then the resulting vector is going to be x1 plus x2, y1 plus y2, and z1 plus z2. And so how do we check if that's in V? Well, what we need to be in V is for x plus y plus z to be equal to 0. So let's check. If I take and add all three of these, x1 plus x2 plus y1 plus y2 plus z1 plus z2, well, x1 plus y1 plus z1 equals 0 because x1, y1, z1's in V. And x2 plus y2 plus z2 equals 0 because x2 plus y2 plus z2 equals 0 because this vector is in V. And so this means we have 0 plus 0, which is 0. So it's in V. Okay, if we try to do closed under scalar multiplication, we take some alpha times x, y, z, where x, y, z is already in V, we get alpha x, alpha y, alpha z. And so here, once again, we'll have alpha x plus alpha y plus alpha z, which is just alpha times x plus y plus z. But since x, y, z is in V, this is 0, so we have alpha times 0, which is 0. So let me rewrite this. This is in V. And this is also in V. So we're going to get our vector properties. We don't have to worry about those. Our additive identity is going to be 0, 0, 0, which is in V. Our additive inverses are going to also be in V. So here we have, if we pick some x, y, z to be the thing, our additive inverse will be negative x, negative y, and negative z. And then our scalar identity, as usual, is going to be 1. Great. So I have one more vector space that I want to share with you guys, and then I think you guys will have plenty of examples of vector spaces to worry about. I want to point out at the bottom of this next page, there is an example vector space of the Galois field. This will hopefully be on a homework eventually as extra credit, but we're going to skip it for now. It's kind of cool. It helps think about binary a little bit. But the last vector space we're going to talk about is the heat states in diffusion and other models. So a manufacturing company uses a process called diffusion welding to adjoin several smaller rods into a single longer rod. The diffusion welding process leaves the final rod heated at various temperatures along the rod, with the ends having the same temperature. So every A centimeters along the rod, so depending on how far we're talking about, the machine records the temperature difference from the temperature at the ends to get an array of temperatures called a heat state. So we want to go ahead and plot these different values in order to look at what a heat state would be and kind of visualize it. So these zeros here are representing room temperature. And so those are always going to be zeros on the end. So let's go ahead and do this. We get 0 there, 1 there. We get a 13 up here, maybe a 14, a 12, a 5. I'm going to wish I had spaced this better. -2, -11, -3, a 1, a 10, an 11, a 9, a 7, and a 0. This is the end of my rod. I don't need any of this other bit. So here we have 14 centimeters length of rod. And we could go ahead and get another example of a heat state for the same rod. So start at 0 right here. Then we have maybe some diffusion of the temperatures. So we had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 dots before. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 dots again. And so when we're looking at these, notice that this is going to be a vector space. And if we want to look at what those vectors will look like, we're going to have a 0 on the end. We'll have a bunch of different values in between, and we'll have a 0 on the other end. So when we're looking at this is going to be a vector space because we could go ahead and add those temperatures. We could multiply them by scalars. We get something that looked like these vectors for our heat states. So the takeaway from this is we have some properties in order to get some vector spaces, and we have some common vector spaces we're going to be working with going forward.